first talk will be given by Luca Galantucci from Newcastle University, and his talk title is Quantum Vortex Reconnections, Crossover from Interaction Between Regions.
Okay. So, first of all, thanks to the organizer for giving us the opportunity to show the latest results we had in Newcastle on quantum vortex reconnections. The work I'm presenting was done in collaboration with Andrew Bagley, Nick Parker, and Carlo. So this is the overview of my talk. I will give a brief introduction, general on filamentary structures, then I will go to more in detail on quantum vortex reconnections, and then I'll address the main topic of our results, which is how the minimum distance between reconnecting vortex strands scales with time. So I'll go through the state of the art, which is like 20 years of work till now, and then I'll present our results concerning crossover, when and why this crossover takes place. So first of all, coherent filamentary structures are present in very many distinct and several physical systems, and they play a fundamental role in all of these systems. So for example, if we take plasma and astrophysical media, reconnections of magnetic flux tubes, they are believed to be responsible for the anomalous heating of the solar corona, and also for explosive events in solar and stellar flares. If we move to polymer physics and DNA, we can say that here the filamentary structures are long chains of atoms, and characterized by the fact that the size of the core is very small compared to the length of these structures. And in this case, however, we don't have any reconnection, but we have some strand passages, so they just flow one towards each other and then gets passed. And this is, for example, some work done by the Micheletti group in SISA in Trieste. Then, if we move to in optics, then there are these filamentary structures are lines of zero intensity, and here, so what is called optical vortices, and they are singularities for the phase of the wave. And so in this case, also some reconnections have been observed between these one-dimensional structures. We also have them in liquid crystals. Here you can see very neatly reconnections of two topological defects, which was reported in Science nearly 30 years ago. And then, of course, we have fluids where these one-dimensional structures are, so where these filamentary structures are either vortex tubes in classical fluids. Here you see here reconnections between those two vortex tubes, and the difference we would see between these types of reconnection and reconnection in quantum vortices are these bridges of mainly second vorticity between the two vortex tubes. And then we have vortex lines, which is, for example, here we have a snapshot of two quantum vortices reconnecting in box-trap condensates. So, what are the differences between classical vortices and quantum vortices? So, in classical vortices, classical fluids vortices can have any shape, any size, any orientation. Their strength, so the flux of the vorticity is unconstrained, and also the vortex core is finite, is arbitrary. So you set the threshold for the vorticity and you get the vortex tubes. So here you can see different types of vortices in different scales, from a cup of coffee to the astrophysics media. However, as we learned also in all these days, in quantum fluids, vortices are a bit different in the sense that they are created with putting into rotation the superfluid or via temperature quench, so the famous Kibble-Zweig mechanism. And they are effectively one-dimensional structures, which are topological defects of the order parameter, which is a complex order parameter. And the vorticity here of the flow is confined to those vortex lines, so to the one-dimensional structures via a delta function. So the vorticity is a distribution centered on the vortex lines. The circulation is quantized in terms of the quantum of circulation, which is given by the Planck constant divided by the mass, and the velocity is given by the gradient of the phase. So in this setting, the reconnections are easier to study as they are well-defined, isolated, and dramatic events, which are different from what I showed before for the classical fluids where you have those bridges. So there are many types of quantum fluids. We've seen this morning neutral stars. There will be talks about helium-3 later on. And we will concentrate in these works in superfluid helium-4 and in Bose-Einstein condensates. So very quickly, and just to show some differences concerning the equations of motion of quantum fluids with respect to classical fluids, from the Gross-Pitarevsky model, which describes the dynamics of a condensate at very low temperatures, a condensate which has to be dilute and where the interactions are weak, for the other parameter I was describing before, we can do the so-called Madelung transformation, and so we can get two equations. One is the equation of mass conservation first, and this is the equation for the conservation of momentum. And we see that if we take a homogeneous Bose-Einstein condensate, so for where there's no where the potential is constant, and we neglect for this term PQ, which is the quantum stresses, we regain compressible error equation. So what is this this quantum stress here? It has this expression, and it is very important on the length scale of the healing length. So when we probe the system at a sufficiently large scale compared to the healing length, this term disappears, is negligible, and so we get we recover the compressible error equation, which, as we all know, forbids reconnections because of the Helmholtz theorem. Therefore, we can say that the quantum pressure term is terms which acts on small scales and which is responsible for quantum vortex reconnections. In fact, so here we have the equation for classical ideal fluids with no viscosity, Navier-Stokes, and quantum fluids. And we see that in the classical error equation, there is no reconnections are allowed, the energy is conserved, and also the helicity, which is a degree of measure of the knottedness of the vortex angle, is constant as the topology is frozen. When we move to the classical Navier-Stokes fluids, so viscous fluids, we see that it is the term involving the viscosity, which is driving the reconnections, and at the same time, it is the same role played by the quantum pressure in quantum fluids. Just to see here that while helicity it can have different behaviors in classical fluids when reconnections occur. After a long debate, as we shall see in more detail in a few slides, in quantum fluids, helicity, if we take into account all the terms, is actually conserved and always equals to 0. So these are quantum vortex reconnections. So that here is schematic. So you see that the color code goes from indicates the color grading indicates the direction of the vorticity. These red and blue arrows show the rotation of the fluid around these vortices, and a vortex reconnections means that you have that the vortices exchange strands, and therefore here they approach and they move away in this fashion. So why quantum vortex reconnections are important? Because they redistribute both helicity and energy among the scale, they enhance mixing, and also they trigger a Kelvin wave cascade on the vortices due to the cusp it creates. And they also are the ultimate mechanism that transforms incompressible kinetic energy into compressible energy, kinetic energy, so sound. And so also in addition to superfluid helium-4, the reconnections are fundamental for setting up a Kolmogorov spectrum of kinetic incompressible energy, which is very similar to the classical spectrum that is observed in classical fluids. So, in 1993, there was the first work, it was a numerical work by Koplik and Levin, which showed that, confirmed the Feynman conjecture that superfluid turbulence had to take the form of a cascade of reconnecting vortex rings. Since then, there has been many works have see if there are some universal features of reconnection. And on one thing that was explored, it was that this universal routes towards reconnection via the formation of a pyramidal cusp. So in their work in '94 by Arts and De Waele, they started from different initial conditions, and they measured numerically the angles phi1 and phi2 of this pyramidal cusp. And the argument was that independently from the initial condition, they would get, after a transient, they would get similar angles. So the fact was, he said that this is a universal characteristic of quantum vortex reconnection. However, nearly 20 years later, a work done by Carlo and collaborators showed that this is not the case, that, for example, the angles phi1 and phi2 actually depend on the initial condition when you throw a vortex ring towards a vortex line. So depending on the positioning of the vortex ring compared to the vortex line, the angles phi1 and phi2 are not conserved. So you see here different evolution of phi1 and phi2 depending on the initial angle. Then there has been also some work concerning the induced cascade of vortex ring by Bob Kerr and by the group of Conrad Bayer. And then also some work, very nice work in Chicago by William Irvine group that showed that the decays of superfluid knots occur only via particular pathways that has to do with the change of the twist and of the right. So with connecting the change, the pathways for the superfluid knots decay to the helicity. So I mentioned helicity twice or 3 times already. So what is helicity? Helicity is the volume defined also in classical fluid dynamics as the volume interval of the scalar product between the velocity and the vorticity. And it gives the idea, it's a measure of how the vortex line entangle, or not also entangle, even if normal knots or few simple structure, they are knotted. So here we have to make a distinction between the singular vortices that we have in, for example, in VCs, so which are described by the Gross-Pitaisky model. So these are topological defects, means that the core, as we have learned in these days, has been showed, it's a hollow core. It goes, the density is 0 on the vortex lines, and the phase, and so also the velocity and the vorticity are not defined. So in quantum, if we want to apply this fluid-like definition in for quantum fluids, we have to do some regularization. This was done by Marc Brachet and collaborators in a few papers. And so, by the means of this regularized helicity, they have studied how helicity evolves depending on the initial condition. And so here, for example, they have considered that it's a hot link, so 2 knotted vortex rings. And here, for example, you have the trefoil here. And here it's showed how, okay, the red curve doesn't show very well. So how the evolution of the regularized helicity depending on the different initial conditions. So the green curve, this one, is a curve where corresponding to the I'm sorry about that. Where shows the evolution of the helicity for the Hopf link, and you see that the green arrow shows the reconnection, and you see that the helicity after small bump is more or less conserved. Here there is a line that you cannot see, but I will trace it. It does like this, the red line, and so it shows that the helicity is not conserved during the reconnection of the trefoil knot. And so the explanation that was given is that the conservation or not of this regularized helicity depends on how the reconnection appears. If the strands align in an antiparallel fashion for some in large extents, which is the case of the 2 rings, then there is a conservation of helicity. Otherwise, the other curve shows that the helicity in this case is not conserved. I have to point out that this type of helicity, which is calculated with this regularized definition, does not take into account all the terms, all the different components of helicity. So helicity, if you take helicity for a classical fluid, you have three different types of contribution. You've got links, which is for example, if you have two knots like in the ring, how many links there are between different vortices, the writhe, which is self-linking, and the twist. In this case, it's the so-called the evolution of the centerline helicity, which is just the sum of link and writhe. This is because with quantum fluids, we have a problem in defining the twist, because the twist, to define the twist, you have to have two neighboring field lines, which of course in vortices which are singular, like the vortice in the GP, it's not possible because we have only the vorticity is only concentrated on one line. This was solved 1.5 years ago by Heider Salman in Norwich, who has done a very rigorous definition of this twist, and according to this definition, we have that for helicity in superfluids is always equals to 0. So it's a conserved quantity, but it's equals to 0. Same with some other work on reconnection was done by William Irvine in Chicago and also David Promet in East Anglia, and conserving the centerline helicity, so neglecting the twist, it was shown that the helicity redistributes the reconnections, redistribute helicity towards the scale. So from linking, you go to calling and then to the twist. Just to mention, in superfluid helium-4, if you do calculation with the Monte Carlo framework, you find out that that actually the core is the density doesn't go to 0. So here you have your red line for the Gross-Pitayevsky vortex, while here you've got it for the in this quantum Monte Carlo calculation, you've got that the density doesn't go to 0, and you have got these wiggles. The consequence of this on the velocity field is that you don't have a singularity, and so you have a constant vorticity, like a Rankine vortex, in the core of the vortex, and then it decays irrotationally. So we have made some calculations in Newcastle showing that helicity in superfluid helium actually gives the measures of the contribution of the non-local velocity. So you have to take for each point along the vortex, you calculate the scalar product between the tangent to the line with the non-local velocity, which is the velocity that all the other line elements produce in the vortex element, and then you sum all over the tangle. In fact, what we find, and here's the reference for someone who's interested, is that, of course, this depends on the strength of this non-local velocity. And so if we have some binding turbulence or counterflow turbulence, where the vortices are more aligned randomly, you have that the contribution is negligible, so helicity is 0 apart from oscillation. But when you go, for example, to a more organized flow, for example, quantum superfluid helium, which is steered mechanically, and you have a Kolmogorov spectrum in the normal fluid, helicity is the value of helicity is non-zero, and is actually much bigger than the one with the invariant turbulence. Okay, so now let's go to the minimum distance, scaling of the minimum distance with time, which is the argument of our results that we had we found in Newcastle, starting from some analytical results which were obtained by Nazarenko and West in 2003, and which have been generalized by a recent paper by Giorgio Krusulovic and David Promet and Alberto Villois in technical collaboration from Nice and East Anglia. And so it's quite simple. So you have the Gross-Pitayevsky equation. When vortices reconnect, density goes to 0, so it means that you can drop the nonlinear term. Okay, you do a simple transformation, so you have the evolution of the wave function is performed via a linear Schrodinger equation. And so starting from an initial configuration of two straight lines, if you go back and forth in time, you see that actually you've got two hyperbolas, and the scaling of the minimum distance is those scales like t to the half. The same scaling can be obtained by was measured in employing solid hydrogen particle as tracers in the Maryland group, and here also it was found in some subsequent papers that also in this case the exponent alpha is equal to 1/2, both pre-reconnection and post-reconnection. So here you can see these are vortex lines tagged with these solid hydrogen particle tracers. Recently, so just a few months ago, there was the experiment was redone, employing frozen air tracers, which are smaller, and in a different setting, which meant that there was no counterflow at all, and so the vortices were more straight, and they were also more isolated, so there were no contribution from neighboring vortices. And what has been found is that actually the distribution of the exponents was a lot more peaked. So it was a lot more like delta going like t to the half, while here you have a slightly broader distribution. So the message here is that when you've got vortex lines which are more straight, and that the interaction with boundaries or neighboring vortices is negligible, you find more robust alpha to the t to the 1/2 scaling. So just to mention, and then I will not spoil Gabriele Ferrari's talk tomorrow, with some work that we have done with the University of Trento, we have studied reconnections in confined geometries, and what we have found is that thanks to an innovative visualization technique, some other interactions are possible. So normally when you throw a vortex toward the other, you expect that these vortices reconnect. Actually, because of the confined nature and inhomogeneous nature of harmonically trapped condensate, you find that it's possible that there are other interactions which are possible, and namely rebounds, ejections, or double reconnection. I will leave to Gabriele tomorrow to explain more in detail this work. So there have been some numerical work on the scaling of the minimum distance with respect to time. And so with the vortex filament method, in their paper 94, which is the paper I was cited before by Arts and De Vaele, they also found that in the approach dynamics, delta scaled like t to the 1/2. Then there has been several work on using the Gross-Pitayevsky model, and they all started from an initial distance of 6 healing length. And then some of them, the most recent ones, tracked the vortex line employing a pseudo-vorticity vector, which is defined everywhere, so not only on the vortex line, but everywhere. And this is the summary of the result. So you can see that I chose only two configurations, so the anti-parallel configuration and the orthogonal configuration. And so you see that this work done by Carlo and collaborators in 2012, the prefactor were different post and pre and post reconnections, both for anti-parallel and orthogonal reconnections. The work by Cecilia Rorai and Bob Kerr and Srinivasan in 2016 showed that there is a symmetrical scaling in the anti-parallel, but again a non-symmetrical scaling for the orthogonal reconnections. While a recent work by Kuslovic and collaborators showed that actually, but in a very robust way, that the scaling is always 1/2. So the message here is that still, till recently, there has been a debate concerning the scaling of the minimum distance with respect to time at very short distances, which has been more extensively and also with some analytics concerned addressed in this work. So actually, the situation now is that it seems that that the scaling of the minimum distance with respect to time goes like t to the 1/2. So here, just to I've plotted all the results in this plot of there is the past results, and in green you can find our results. So this the delta is normalized with the core of the vortex for helium and the healing length for the condensates, and here this is normalized by a time scale which is given by the ratio between the core and the speed and the speed of sound. So this is the experimental results. These are the vortex filament numerical results, and all of those concern the GP. So here is our simulation with the vortex filament method, which I'm going to explain, which seems suggesting that there is a crossover, or like here. Why? In the next slide, I have summarized all the Gross-Pitayevsky simulations. So you see that this is where, for orthogonal reconnection, so you see that this is the case where it's 1/3. Then you've got this one is little, so the Bob Kerr's results. Here we have Carlo's result, which is nearly 0.4, and this is the 1/2 scaling with the blue stars by Giorgio and others. So first, let's start with the dimensional analysis. So if we suppose that the minimum distance depends on several parameters, so a physical quantity. So the time, of course, quantum of circulation, a characteristic length scale, density, and the gradient of the density. And if we do a very straightforward dimensional analysis employing the Buckingham-Pi theorem, we've got that you can have three different scalings. So this one is the dimensional scaling that was argued also in all the past work, which means that the only relevant parameter that counts is the quantum of circulation. And so we have t to the 1/2. These other two scalings are linear scalings and mean that you have a characteristic velocity. So we have to, here, these scalings, characteristic velocity is introduced. And so by mean of characteristic length scale, which can be, for example, in a vortex ring, it can be the radius of the vortex ring, or if you have a trapped condensate, a box trap, it can be the distance from the vortex image which is driving the vortices, or in this other characteristic velocity is the velocity is indeed the velocity given by inhomogeneous density field in a trapped condensate. So already here we see that there is another possible scaling. So apart from t to the 1/2, also a linear scaling here. So the characteristic of the present work are the following. We analyzed with the Gross-Pitayevsky and the Vortex filament method reconnections in both Bose-Einstein condensate and superfluid helium. We started with a larger initial distance. So in the Gross-Pitayevsky from 10 healing length to 100 healing length, and the Vortex filament method from 10 to the 6 to 10 to the 7 times the vortex core. We addressed reconnection in both homogeneous quantum fluids, so in the idealized setting of infinite and unbounded condensates, and also in confined condensates, which are the experimentally accessible condensates, so the one confined by harmonic traps and the more recently designed box traps. So these are the difference between the Gross-Pitayevsky model and the vortex filament method. Actually, this has already been described very well yesterday in Carlos' talk. So the main difference is that here the vortices are topological defects of the wave function, and here we probe the fluid at length scale which are smaller than the vortex core. So we are able to see the density depletion created by the vortex core, and also we are able to account for compressible effects of sound waves. And these models, the reconnections in the Gross-Pitayevsky model are solution of the Gross-Pitayevsky. On the other hand, with the vortex filament method, it is a mesoscopic model where probes the flow at a very larger length scale. It is incompressible, so we cannot be able to describe compressible effects. It employs the Biot-Savart law, and therefore, as we know, in an Euler fluid, which is the description of given by the Biot-Savart law, no reconnections are possible. So what we have to use an ad hoc reconnection algorithm, which means that insert to some length scale, the results with the vortex filament method are not reliable, and we will see that in a moment. So, homogeneous Bose-Einstein condensate. We chose two different settings, which are quite relevant for both Bose-Einstein condensate, but also for helium, as we should see. So, orthogonal vortices and a ring thrown towards a vortex. And we chose the orthogonal setting because in order to compare results with past studies. So these are two limiting cases, but which we reckon fundamental, and which we shall see. They produce the fundamental scaling for homogeneous superfluids. And this is because in this case, we've got two vortices with comparable but negligible curvature, while in this other setting, the curvature of one vortex is significantly larger than the other vortex. And this is quite relevant for superfluid helium-4 at low temperatures, where the low density of the thermal fluctuations are not able to dump out small vortex structures. So if we take the results with the orthogonal vortices, we see that more or less they broadly align also at large distances on the t to the 1/2 scaling. So here you have this plot has to be read in this way. So This is the pre-reconnection. Here you have a reconnection, and then this is the post-reconnections curve. We see that for very short distances, the scaling goes like t to 1/2, and this is both in the pre and the post-reconnection dynamics, and this is consistent with the Nazarenko argument saying that when vortex merge, we can throw away the nonlinear term and we'll get the t to the 1/2 scaling. This is also consistent with the most recent Gross-Mitteiski simulation, but not with some of the older one that I showed before. So because we have a certain range of distances, we calculated the fitting exponent of this power law. And so we did find that for short distances, we have a scaling exponent very close to 1/2. It deviates in the central, in the intermediate distance. And then at larger distances, for the post-reconnection, we still find 1/2. To understand, to map when these deviations from the 1/2 scaling, we have calculated the contribution of the local curvature to the approach velocity. So how did we do this? So we took the 2 points at minimum distance on the 2 different vortices, and we calculated the vortex of curvature, and then we approximated the velocity stemming from the local curvature as the velocity which would have a vortex ring with the same radius, which is this one. This is the binormal. Then we made the difference to a relative velocity, and we projected the results on the separation vector. And so this is what we have called V gamma, and then we divided by the total approach of separation velocity. So here the red curve describes the pre-reconnection dynamics, and the blue curve describes the post-reconnection dynamics. So if we put everything together, what we can say is that where the contribution of the curvature is important, you've got the most deviation from the t to 1/2 scaling. At the same time, here in the post-reconnection, where the vortex contribution is lower at larger distance, we recover in fact the t to the 1/2. So how is it possible to put together the fact that the Nazarenko agreement gave t to the 1/2 when the nonlinear terms was negligible, so when density went to 0, with the fact that we have 1/2 scaling at large distances? Well, if the driving dynamics, which puts the vortices together and makes them separate, is actually the mutual interaction, from the Biot-Savart law, we get immediately the t to 1/2 scaling. So this means that when you have t to 1/2, you have either the mutual interaction is dominant, or you have that density goes to 0. And actually, these are not contradictory, because actually the fact that you find t to 1/2 at short scales can be explained both with the fact that the density goes to 0, but also that at so short distances, the predominant dynamics is the mutual interaction between the vortices. So we move to the ring line reconnection, and this is important, as I said before, for superfluid helium at low temperatures, because small vortex structures are not damped out by temperature. In fact, we know that turbulence is like in Golov in Manchester. In Golov experiments is generated by injecting vortex ring. Vibrating vortex structures that create turbulence involve many reconnections between small vortex ring and reconnections. And also the collision between vortex ring and vortex lines are important in homogeneous quantum turbulence. And also superfluid boundary layers produce a lot of small rings which reconnect with vortex lines. So what we found is that we started with we did 3 simulations with 3 different initial radius with a constant initial distance, and we see that we have 2 scalings. So one t to the 1/2 again at small distances, and one linear scaling at larger distances. So in what sense, if we compare with the dimensional arguments that has been illustrated before, we have that this coefficient is given by the square root of the quantum circulation, and here this other coefficient is actually given by the velocity determined by the vortex ring. It is in fact it is reasonable to associate the constant derivative with respect to time of the minimum distance at large distances with the velocity of the the constant velocity of the vortex ring with which the ring travels with, towards the vortex line. And so we can write this, the derivative of delta with respect to time, like constant c times a function of the radius only. And therefore, if we plug this into the previous equation here, we get that delta scales in this way. And in fact, in the inset, if we divide delta with the function of with the function f, which is different from depending on the radius, we've got that the three curves here in the pre-reconnection, they effectively collapse at large distance. So the question is, what is the crossover distance that makes the scaling change from t to 1 to t to 1/2, and why? So we again go back to the contribution of curvature, and so we see that when the velocity stemming from the local curvature is nearly the only factor in thermodynamics, we've got t to the 1, and again, when the velocity, the curvature contribution drops, we again find the t to the 1/2 scaling. So it is possible to say that we have this crossover between these two scaling in the pre-reconnection when there is a change in the balance between self-driven dynamics stemming from the vortex ring motion at large distances to the mutual interaction which determines and governs the dynamics in the short scale. So what we argue here is these are two fundamental scaling. So of course they can be intermediate regions, intermediate cases where the curvature plays a role, and we have seen that, for example, in the orthogonal reconnection, the velocity contribution is responsible for a deviation, but these two scalings, in our opinion, show the most representative scaling, so the trends at which the vortex reconnection minimum distance scaling tends depending on the balance between mutual interaction and self-driven dynamics. So just to mention, if you look at the post-reconnection situation, you just find that only for the smallest vortex ring, you find that it is the t to the 1 scaling is recovered at large distances. This is because when, I'll show you in a video in a while, when the vortex ring reconnects with the vortex lines, what is created is a small vortex ring, which is actually an elliptical vortex ring, and which therefore wobbles. And here you see these are the minimum and maximum and minimum radiuses of the vortex ring, and in fact you see that when the oscillations, which produces sound and which makes the energy of the vortex ring decrease and so its length, when these oscillations stop, in fact you recover the t to the 1 scaling. On the other side, with the radius, the biggest radius is still oscillating when t is equal to 10 to the 2, and in fact in this case the t to the 1 scaling is not recovered. Just one last thing to put together the Nazarenko argument about vanishing density and the mutual interaction between vortices, both of which produce the t to 1/2 scaling. We see that this is the density along the separation vector. So you have to imagine that if you fix time, here you have the density on the line going through the 2 points of minimum distances. So the black is of course the vortex core. And so you see that when you go towards the connections, you see that the t to 1/2 scaling sets on here, where still density is not negligible, but then it still holds when density goes to 0. So this means that the Nazarenko argument and the mutual interaction argument, which give the t to 1/2 at short distances, they are consistent. We have the very same results if we take the vortex filament method, so which analyzes the vortex reconnections in superfluid helium. Of course, the distances involved are different, and only the values of delta greater than 2 or 3 times the discretization of the vortices are reliable, because of course the reconnection is made employing ad hoc algorithm. And so we see that for orthogonal vortices, we've got t to the 1/2 both pre and post. We see a clear crossover between t to the 1 and t to the 1/2 in the pre-reconnection with the ring between the ring and the line. While in the post-reconnection, things are a bit messy. So we might see T to the half, but actually there are Kelvin waves, so we don't pretend to say that to explain this with the predominance of the mutual interaction dynamics. So very quickly, we moved also to trap BoseEinstein condensate, both harmonic traps and the more recently designed box traps. We'll show only the results concerning the harmonic traps. So we put two orthogonal vortices on radial planes intersecting the axis of the condensate, and at different initial distances. And we know very well that they process on an elliptical trajectory orthogonal to the vortex itself. And the only parameter determining the dynamics is the so-called orbit parameter, which is the ratio between the position of the vortex and the Thomas Fermi radius. We know also that outer vortices move faster, and so what we have investigated the scaling of the minimum distance with three different values of the orbit parameter, which on the basis of the work done with Gabriele Ferrari and his group, we know that with these values of the orbit parameter, we will have a reconnection. If we choose smaller values of the orbit parameter, we might have a rebound or a double reconnection. Here, the minimum distance is scaled with the healing length valued at the center of the trap. So here again, we find that there is a crossover. And this is because it is possible to introduce a characteristic velocity, which is the velocity stemming from the gradient of the density, which drives the vortices in the trap. And here this is only the pre-reconnection curves for different values of the orbit parameter. And here in the inset, I just reported the pre and post reconnections at very short distances between for two different values of the orbit parameter. And we see that the increase of the velocity between pre and post reconnection is greater as the orbit parameter is smaller. So this means actually that because when the orbit parameter is smaller, the reconnections occurs more in the center of the trap. It means that the density, where the density is higher, it means that the density plays a role, and therefore that sound emission should be one of the responsible of this increase of the velocity. And in fact, this is a cut through the condensate just after reconnection. So the blue are the intersection of the vortices through this plane, and this in yellow is the rarefaction pulse which is emitted by the reconnections. So here, if we try again to explain what is this constant velocity which drives the vortices together, and we expect that this approach velocity is proportional to this function of the orbit parameter. Why we chose this type of function is because both the velocity driven by the density gradients and the velocity stemming from the curvature, because in our case the chemical potential is still, because of computational resources, is still small. The vortex is curved while it travels toward the other vortex, and in both cases, both of them are proportional to this function. And in fact, if we divide delta by this function of K, we find that they collapse at larger region. The same collapse can be found if we rescale the delta by not the healing length in the center, but by the healing length at the reconnection. So we find that if we compare with the previous slide, where they were separated here, the three lines, they again collapse in a small distance. So the conclusion, we've made a vast numerical campaign employing both the Gross-Pitayevsky and the vortex filament method. We address both homogeneous system and experimental accessible trap condensate. That the initial distance is significantly larger compared to previous studies. So we found that for smaller distances, we have a T2.5 scaling, which seems to be now universal because it's confirmed by several studies, the more recent studies. When at larger distance, we can have two different behaviors. One is T2.5 is still the mutual interaction is driving the vortices. or we have a linear scaling if it's possible to introduce a characteristic velocity scale. In this case, we have a crossover, and the crossover is determined by the balance of these two different effects. Interestingly, in trapped BC, so not only in the harmonic traps that I've showed, but also in box traps, we always find a linear scaling. So we argue that this is the situation, and that t to the half and t to the 1, as already said before, are fundamental scalings, which are limiting cases, but we still, we think they show the trend depending on the balance between the different effects. So the self-driving, for example, a vortex ring, or the the motion of the vortex given by the density gradient, or the mutual interaction. So this is the future work. I will leave you with that, and thank you for the attention.
We may have time for 1 or 2 questions, quick questions. Go ahead.
I was just wondering, so you have these 3 different, or the trap case, where you build the proportional to the power 1 scaling. So there's the 3 different contributions, but then there's some sort of balance between those, which still gives you the 1 scaling. For the trap AC case, you'd expect that the image chart was important, as well as the density curvature, I suppose. So how can I
so the thing is that in top condensates, there's been let's say probably still ongoing the fact that if the image drives the vortex or not. So there are, as you know, there are several papers by Fetter who says that now things are a bit changed. The fact is that here you have both. Both the density gradients and the curvature, which also link to the distance with the image, because the curvature is a function of the distance from the boundary. If you do a simple calculation, they have the same effect. So now, if you're asking me which of the 2 in this case is driving more the vortex, I'm not sure what to answer, because the fact is that you should do it with different trap geometries to understand.
Yeah. All right. Any more question?
One question.
Okay, one last question.
After reconnection, the vortex lines should become shorter. How shorter they really became?
This is the argument that is used for the ad hoc reconnection algorithm. Actually, in this case, they get shorter on the vortex here, and they get shorter because you use this algorithm, and so it gets shorter on the
vortex score.
On the vortex score on discretization along the vortex. On the BC, in case of the Gross-Pitaevsky, actually vortex curve, and so there's an increase of length just in the middle of the reconnection.
How can you increase length? It should emit sound and lose energy. Therefore, the length must.
Yeah, but the energy is proportional to the length only if you have an unbounded system. Here, here the energy when two vortices get closer, as you well know, and get anti-parallel, the energy of those 2 vortices goes dramatically down, right?
Okay. All right. Let's thank the speaker here. We'll have a coffee break.